Hi, everyone. It is indeed a privilege tonight to have with us um, Dr. Benjamin Taylor. Okay, Dr. Benjamin Taylor was with Chica's group at Lancaster University previously. He is now the lead data scientist at Blackpool Teaching Hospital, NHS Foundation Trust. I've known him for a number of years. A brilliant guy, and he has written a few R packages, especially in for statistical modeling. He's a Bayesian guy, basically. He's a Bayesian guy. Um, so I think without further ado, I'll stop the sharing of the slide. So what we're gonna have tonight or noon there is 40 minutes presentations from Dr. Taylor. And after that, following that, we will have a 10 minutes Q&A. So Ben, the floor is yours. I'm going to stop sharing my screen and you can share yours.
Great, no worries, yeah. I'm just waiting for it to appear.
Yeah.
It's still grayed out, is that normal or?
All right, okay, let me change this.
Great, that's fantastic, thank you.
All right. Sorry, I just,
That's all right.
Just put it as, as grayed out just to make sure that there's no one going to zoom what we call zoom hackers something like that. Sorry, Ben. So over to you.
Lovely,
We
thank
can
you.
see your slide now.
Let's pull this down here. So can you see that okay? Can you see my mouse as well?
I can see the Cisco WebEx. I couldn't see the mouse. Are you using two screen, Ben?
I am using two screens, yes. Is that going to be problematic?
Yes, now I just saw the mouse there.
Great. Okay. So can you see me underlining the title with
No,
the mouse?
not yet. Not yet.
Not yet. Okay.
Okay,
I
can see the mouse now just disappear.
Okay, so it's coming and going. Okay, that's fine. Just wondering if I can just put this at the bottom here. That might be. Can you see it now? That's on the screen.
I can see your screen, but I couldn't see the presentation yet. The slide is not there yet.
The slide's not there. Okay, let me see if I can just try that again. Try sharing again. Let's have a look. We did try this the other day, everybody.
Yeah,
and it works nicely.
Don't worry, take your time.
I'm not sure how to do this.
You can, when you click the share button.
Is it sharing? Can you? Is that because? So if I bring this down here.
Yeah. Yep. Now I can see. Now we can see.
Now you can see it. Now I understand. Okay. Oops. Okay. Yeah. I shared the wrong screen. That's what it was. No, I don't want to do that. Let's cancel that. No, I don't want to do that. Why is it not letting me? No, I don't want to leave the meeting.
To maximize the edit reader, Ben.
Yes, I'm sorry. I'm not used to Windows. I'm a Linux user, so I'm having to try and find out where.
Then I think You can go to view and then
View. Ah, got it. Full screen mode. Brilliant. How's
excellent.
that? And you can see my mouse as well.
Brilliant. Looks good.
Okay, fantastic. Okay. Right, thank you. Thank you very much. Sorry about the confusion there at the start. First of all, very warm thanks to Cameron. It's lovely to come and present on this webinar, and I really appreciate the invitation. It's lovely to see you again, and it's great to go out there and talk about something that I'm kind of deeply interested in a sense. So Cameron asked me to give a presentation on Bayesian statistics, a relatively introductory presentation. And I thought, well, the way to go about doing this would be to talk about what is Bayesian statistics, why might you want to be Bayesian, and when and how you might go about being Bayesian. Obviously, 40 minutes is a relatively short amount of time to kind of cover a massive topic, and this is really only scratching the surface. But I hope you'll find it useful, especially if you haven't used Bayesian statistics before in your research. I would say, at any time, please do interrupt me. And please feel free to ask questions. I'm very happy to answer questions as I'm going along. And if you're stuck on something, it's likely that somebody else might be as well. So it's probably best to just resolve that as we're going along. So probably despite what Cameron said at the start there, although it's true that I really like Bayesian analysis, and even I'm probably passionate about it. I'm not dogmatically Bayesian, which means I don't think it's the be all and end all of all statistical analyses. I will sometimes use frequentist methods, and sometimes I'll use Bayesian methods. I really like the Bayesian paradigm, and perhaps I communicated some of that enthusiasm to Cameron whilst we were working together in Lancaster. I hope so. So I'm going to talk a little bit about both of these areas, really, because I don't think you can talk about Bayesian without also give an introductory presentation on Bayesian without also talking a little bit about frequentist statistics. So the name Bayesian, it comes from a guy, the Reverend Thomas Bayes, who lived back in the early 18th century. So the famous Bayes theorem is named after this minister. But in reality, it was early times then, and actually, Bayes actually really didn't contribute that much in practice to the theory of Bayesian statistics. He elaborated one special case of what's now generally known as Bayes' theorem in one of his theses. And it was later on that mathematicians such as Pierre Simon Laplace popularized the idea of Bayesian statistics. But again, the subject has grown really enormously in the last 20 years or thereabouts, 20 or 30 years. It's really become popular, especially tying in with computational advances as well, so computers, programming, that kind of thing. It's perhaps unsurprising that Bayes didn't contribute that much to the theory of Bayesian statistics. He was a polymath. He was interested in philosophy, theology, and other things. But moreover, and perhaps more importantly, the fundamental thing that's kind of underlying Bayesian statistics is a notion called conditional probability. And, a really theoretically rigorous underpinning of this area wasn't really achieved until the 20th century. And because a lot of Bayesian work, especially more interesting Bayesian work is tied in, as I said, with computational advances. It's only really the latter half of the 20th century where it's really taken off, and especially, as I said, in fact, during my career, really. In fact, it's kind of interesting to reflect back on how perceptions of Bayesian statistics have changed in the last 15 years or so. So I was a master's student in Leicester back in 2005, 2006, around that kind of time. And at that time, there were a few rebel Bayesians in our medical statistics group that were teaching the course, and they, obviously I grew very fond of this area of statistics and have contributed little bits, tiny bits, really, into it. But at that time, it was, especially in the medical profession, it was kind of regarded as a bit of a dark art, and I'll come on to why that was the case later on. But I think gradually over the last 15 or so years, that's changed. And in fact, really since about 2010 onwards, there hasn't really been, Bayesian methods and frequentist methods are both perfectly acceptable. And widely used across all kinds of areas. And it's thanks to, the kind of some of the dogmatic Bayesians, some of the people that definitely want to push this area forward, that's kind of kept that momentum going. So I want to start by talking a bit about conditional probability. That's I'm not going to go into the rigorous depths of this, but just to get you thinking about what do we mean by this. So let's suppose we roll an unbiased 6-sided dice. We roll the dice. What's the probability that we've rolled a 6? So that's quite straightforward. There are 6 faces, so it's just 1 in 6, and it's not biased. But let's suppose we want to know what's the probability that we rolled a 6, given that the number was strictly bigger than 3. Okay, well, that's no longer a 6 because we have some information now. We know that the number rolled was bigger than 3, and there are only 3 numbers bigger than 3 on a dice, 4, 5, and 6, and so it's 1 in 3. Okay, so conditioning on something changes what that probability is. And conditional probability is kind of at the foundations of Bayesian statistics. Okay, so this was an example of a conditional probability, and I want to introduce some notation. I semi-promised camera rule that I wouldn't be overly mathematical, but it's kind of difficult to talk about Bayesian statistics without having some equations. But I've tried to limit those to as smaller number as possible, really. So when I write the P here, so P, a 6 is rolled, given a number bigger than 3 was rolled. Okay, so P is the probability that, or the probability of, the kind of vertical line is red given, but it means, as I said, something deeper. It's the action of conditioning on something, and that notion of condition is actually quite a deep idea. We're conditioning on an event here, and that event is that the number rolled was bigger than 3. Okay, so that's what this means, and I'm going to be using this kind of notation throughout this talk. So the probability that a 6 was rolled, given that the number rolled was bigger than 3. Okay, so I need to talk a bit about, before I introduce Bayesian statistics, I need to talk a little bit about what frequentist statistics is, and essentially what the goals of that are and what its philosophy is. But before I can do that, we need a model, and it's interesting. Again, kind of coming from my own education, statistics education. I'm not sure how it is in Malaysia, but in the UK, for example, in schools we're taught things like chi-squared tests, t-tests, and things like that towards the end of our school years. And you never really get to, at that age, you never really get to interact with statistical models for things. But the fact is that there's always a model. Behind the statistical test, there is a model. There are assumptions that need to be met in order for the test to be valid. So things like t-tests, chi-square tests, there is a rigorous probabilistic underpinning for these tests. It's just that when you're taught them at school, that's hidden from you. I don't know whether it's the same in Malaysia. It's certainly the case in the UK. Yeah, so there's always a model in the background, and I always like to think about really simple models to begin with before really complicating things. So let's suppose we had some data that look a bit like this. I hope you can read these axes okay. I've just stuck with X and Y here, but you could think, I mean, for some change in the units, it might be height versus weight or something like that. Something where there's kind of a putative relationship here, perhaps a linear relationship. If you look at the data, it looks like there might be some correlation between the X's and the Y's, and we might want to model those. Okay, so we have pairs of coordinates, X and Y. In this case, there are 30 of these data points. So the xi's and yi's, they're each of the individual points. I goes from 1 up to 30. Yeah. So these are the dots. And we can postulate a simple linear regression for this model. And an ordinary least squares regression would make the following assumptions. So you would assume that the yi's are the outcome here, in a sense. They are the dependent variable, and they might be related to the x's. There's a slope, so an m times the x's plus the c's. So m is the slope and c is the y-intercept. And about that line, we're going to put some normal noise. Okay, so and that noise is constant across the x-axis. Okay, so the amount of noise here is the same as the amount of noise here, is the same as the amount of noise here. So I'm sure you've all at least heard of this before, or even used these kinds of models before. So the y's are the outcome. We've measured those. We know what they are. We've also measured the x's, so we know what both of those are. Now the unknowns here, the unknowns are the parameters m, c, and sigma squared. So m is the slope, c is the intercept, and sigma is the standard deviation of the points about line. So sigma squared is the variance of the points about that line. We're assuming here, so IID here means independent and identically distributed, which just means that so if you think about the difference between this point here and this line, there isn't a relationship between points close by to this one. So there's no correlation between these. They're called residuals, the difference between the point and the line. Yeah. Now the true, so I've simulated these data, so I know what the true values of m, c, and sigma squared are. That's the red line here. Now, what frequentist theory says is, okay, there are some best, in a sense, values for m, for c, and for sigma that these data have come from. Brackets assuming the model is correct. And these best values are fixed. There is a true model. There is a true set of parameters that created these data. Now, although we, as I said on the previous slide, that they're not known, these parameters are unknown, we can nevertheless estimate those parameters with some means of capturing the uncertainty. And if we go and fit an ordinary least squares regression model by just maximum likelihood, then we get the green line. And so so it's not the same as the red line. It's slightly different. That's fine. What you would expect is that the more and more data we collect, so there's only 30 data points here, but if we had 1 million data points, we'd expect the green line to get much, much closer to the red line, assuming the model, again, is the correct model. And so this is the kind of theory that underpins frequentist statistics. But I need to be a little bit more precise still before we can progress here. So our model was that the observations, the y's, they are normally distributed. with some mean. So the mean is the m times x plus c, and some variance about that mean. Okay, and we can write that model as the probability of y given the values of m, c, and sigma here. Now, statisticians are really terrible for notation. So my undergraduate degree was in pure mathematics, and pure mathematicians are really particular about the way they notate things, and it's always easy to follow it. And when I started out my career as a statistician, I promised myself that I would carry on this rigor into my statistical career. But as time has gone on, the traits of the profession have eroded these kind of ideals, and you start to take shortcuts. And so I apologize about some of these shortcuts, but I hope it will be clear what I mean here. So what I've done is I've just subsumed all of these little y's, all of our data points, into just one big y here. So I can talk about y being the data. So in a sense, this is the probability of the data y given the parameters m, c, and sigma, or the probability of the data conditional on the parameters. So this is the likelihood. This is our model. Those two things, when we talk about a statistical model, we're talking about a particular form for the likelihood function. This is the likelihood function. So you'll notice that I've not included x here, even though there is some dependency on x in the data, and that's because we're treating the x's as fixed. They're a fixed quantity, and our variable here, our dependent variable, are the y's. So there's something a little bit subtle about that, and again, in the Bayesian paradigm, sometimes we might want to relax that assumption that the x's, and in fact, you can do this in the frequentist framework as well. In a sense, it's easy to do it in the Bayesian framework. You just add an extra hierarchy to your model. Again, that's kind of a bit beyond the scope of this talk, but those kinds of things you can deal with in a very nice formal framework using Bayesian methods. So the x's we're going to treat as fixed for the both in this case for both the frequentist and the Bayesian versions of this model I'm going to present. Now, because we can write down this model, we can write down the probability of y given m, c, and sigma. What that means is that we can feed in any parameters that we like, any m, any c, and any sigma, and we can work out the probability of the data given those parameters. In fact, technically, it's proportional to the probability of the data given those parameters. But again, we don't need to worry about that too much. So all you have to do is plug these values into the equation. And so if we had some method for searching the space spanned by our m's, our c's, and our sigmas, hopefully we could find a combination that gives the biggest probability. Okay, and there are lots of algorithms to do that. Newton's method is one, but there's all kinds of. Sometimes you can maximize these things analytically, and in the case of an ordinary least squares regression, this is one such instance. So the maximum is a really fun for those of you that have studied any calculus, sort of higher level school calculus. It's a fun exercise to try and work out the regression equations for yourself, just on the basis that you have to minimize the squared errors, so errors between the data points and the line of best fit. But there are various ways to find these M's, C's, and sigma hats. And we put a hat above to denote the fact that it's a maximum likelihood estimate. And that's kind of a sensible thing. The combination of M, C, and sigma that maximize the likelihood over the range of those parameters. Now, of course, because we don't know what these parameters are in truth, and we only have a finite data sample, there's going to be some uncertainty surrounding those estimates. And what we use in the frequentist world is the frequentist theory to derive estimates of the uncertainty around those parameters. Okay. we measure and report that error using a thing called the standard error. Almost certainly anyone that's read a research article will have come across the idea of a standard error. But the standard error is what that is. It's the square root of the variance of a parameter estimate, like the m hat, c hat. But in the case of sigma here, it's a bit more complicated. You wouldn't normally report a sigma, a standard error for something like a variance parameter or a standard deviation parameter, because of the fact that those parameters have to be positive, so they can't go negative. You can't apply normal theory to that. Okay, so any questions just before I move on to the Bayesian version of this? Any questions on the frequentist side?
Any questions from the floor? I mean, you are free to unmute yourself. This is not a webinar, really. This is a WebEx meeting where you can, you can speak and ask questions to Ben. All right, no question yet. Ben, they are fascinated by your talk.
Excellent. Okay. So let's move on then. Now, Bayesians would approach this problem in a slightly different way. Okay, so they'll still look at these data and they'll think, oh, maybe there's a linear relationship between these variables. And so they might write down a model. So the probability, again, of the data, y, given the parameters. And it would be exactly the same as the frequentist model. Okay, but from this point, they would do two things differently. Now, the first of those things is rather than treating m, c, and sigma as some fixed but unknown quantities to be estimated, they would treat those quantities as random. And that is done, that's achieved by assigning a prior probability to the density of all of the model variables. So that's the m's, the c's, and the sigmas. And what that prior probability density does, if you're not familiar with what a probability density is, think of a histogram of those parameter values. So some might be more likely than others, for example. So this prior captures our prior beliefs about the parameters before we've seen the data. And we notate that as follows. So we might write it as P of m, c, sigma. So that's the prior for m, c, and sigma, the probability of m, c, and sigma. So for any combination, we can write down what that probability is. Probably more common is to separate these things out into separate priors for each of the parameters. And again, in the Bayesian framework, that's a modeling choice that you would make. So, for example, and indeed in the code that in the example I'm about to show, we might assign normal priors, so Gaussian distributions for m and c, and an exponential distribution for sigma. And again, the reason for having a different distribution for sigma is because sigma is positive. It's a variance. It's got to be bigger than 0. Other choices we could use here, we might say that the log of sigma has a normal. So sigma has a log normal distribution. But there are other things, gamma, inverse gamma. Essentially anything that's positive will work in a sense here. But you've got to be a bit careful. There are subtleties. And I chose exponential here essentially because that's what our Stan implemented by default. And it's a sensible prior. Okay, so the first thing they do is they treat the parameters as random rather than fixed. And the second really big difference is that they use the posterior probability density for inference. Okay, so the posterior is this sort of inverse probability. It's the probability of the parameters given the data. So it's the probability of m, c, and sigma given y. And this is why it's called Bayesian statistics. We use Bayes' theorem to calculate this probability. And so Bayes' theorem says that we can write our posterior probability density. So that's the density. I'll come back to that. So we can write that as the likelihood here. So this is the posterior. So the probability of y, the data given the parameters, so that's the likelihood. We've seen that before. That was in the frequentist model. It's the same thing. Times the prior, so that we've made a decision on that, on what our prior beliefs are going to be, and divided by P of y here. So that's the probability of the data. In fact, that thing's called the marginal likelihood. And it's a bit beyond the scope of this presentation here. And because it's not necessary for inference, I'm going to ignore it for now. But it is used in model selection. And in the Bayesian framework, that can be done in a very neat and natural way. Model selection, that is. So rather than just a maximum likelihood estimate and standard error, our posterior probability density captures the full probability density of all of the model parameters, the joint probability density. Whereas the priors, they capture our beliefs about the parameters before we've seen any data. Okay, so the posterior captures how our beliefs should change in the light of the data. So we start with a prior, we observe our data, we start with the prior and our model, we observe some data, and then we decide how our beliefs would change based in light of seeing the data. And that's the posterior. That's the thing that we summarize. That's the thing that we use to make inference. And it's quite difficult to see actually this, but I've overlaid the Bayesian estimates of this line of best fit on top of the frequentist estimates, and actually in this case they're nearly identical in this case. Okay, and that's probably because these are simulated data. You know, the model is a good fit. In fact, it's the data exactly come from this model, and in real life situations that is never the case. If you've heard of the saying, there's no model that's the true model, or all models are wrong. I would add to that some are useful models for delivering information that we can use to make decisions. But no model is perfect. So when we run a Bayesian analysis, we don't just get an estimate of the mean and the standard error. We actually get a full-on probability distribution back. And the way that these have been calculated, so I used the R package, rstan-arm, to run the model and report back on these probability densities. And it uses a technique called MCMC, and I'll come back to that a little bit later. But what we can do is, so our intercept here, that's the C. So X here, that's actually M, so that's our slope, and the sigma here. So you can see that these things are summarized by these densities. And in fact, moreover, these are what we call marginal summaries of the posterior. So they're separated out into different histograms here. But in reality, what you have is what's called the joint posterior, which is in this case, a four-dimensional thing, 3 axes, and then the probability of that on the other axis. So we can ask what the probability of any combination of these parameters is. And that's subtly different from asking what the probability is for each one of these separately. Okay, so we get a full-on probability density back. And the other thing, I'm not sure how well that comes across, whether you can see the lines here. The other thing that we like to do in Bayesian statistics for reasons that I'll come on to is we like to compare the prior and the posterior. And this gives a sense of how much information there is in the data on the parameters. Okay, so what we'd do is ideally you might do this with histograms again, or density plots, but you can see here that these are, is it the box, like a box and whisker, or centroid and whisker plots. It's a bit it might be a bit difficult to see, but you can, for the prior here, the range for this red parameter is quite wide on the axes, whereas the posterior is actually very narrow. Similar for the green, so the green is about the width of one of these grid boxes, and again the posterior is very narrow. And the blue here, again, that's roughly the width of one of the boxes, but again it's quite narrow in the posterior. And what that shows is that the algorithm that's being used here has learned something about those parameters. Now, if there wasn't much information in the data on those parameters, then the prior and the posterior would look similar. So it wouldn't have moved, and that would tell you that there's no information in the data on the parameters you're trying to estimate, which is actually a really interesting and useful thing. I mean, you kind of get this from standard errors in the maximum likelihood setting, but this really does tell you something. It's almost an exploratory tool as well, to tell you something about your choice of prior. So I'm sorry, my son is in the background here. Jess, could you go, please?
Don't worry, Ben. Don't worry.
Okay. Okay. So I'm sorry about that.
He's free to join us, you know.
He's got a keyboard in the background, so if some music starts up, that'll be why. So the Bayesian equivalent of a confidence interval is called a credible interval. And rather than presenting things as mean plus or minus 1.96 times the standard error to give a confidence interval, we'd normally in the Bayesian setting use the median and quantiles of this probability distribution. Okay, and it's probably because the Bayesian framework yields these probability distributions that this is the case. It's not necessarily the case that these distributions, I mean, if you look at this one in particular here, that for sigma is clearly not normal. There's some skew, it's skew here in this direction, and this one's maybe slightly skew in that direction. So confidence intervals based on something symmetric, like mean plus or minus something, won't capture things quite correctly. And it's just as easy to compute the quantiles from a sample as it is to compute their mean and variance if you have a computer. And so we usually report medians and quantiles in a Bayesian analysis. Now, one of the ways of going about getting these probability densities is using sampling-based methods. And one such sampling-based method is a technique called Markov chain Monte Carlo. And what that does is it produces samples from the posterior density. And the nice thing about that is it's extremely generically applicable. So you can have one good MCMC algorithm that can answer essentially, almost all modeling questions. So the same algorithm could be used for a linear model as could be used for a hierarchical model as could be used for a missing data problem. So MCMC is one way of getting at these densities. And once we have a sample from our posterior, we can start answering really, really interesting questions. And this slide is as mathematical as it gets in this talk. But there's a really key result, and it's a really beautiful result, really. What this says is that expectations of functions of the parameters in the model, so theta here are the parameters, which might be m, c, and sigma, or some other collection of parameters. So expectations of functions can be approximated just by empirical means. So you can take your sample, you can take the mean of the m's that you get, and that is an estimate of the expected value of m. That's the thing that you would get out of a frequentist analysis. You can do other things like take the variance. I'll just come to that slide in a second. But the important thing about this theorem is that the more samples you collect, this converges to the correct expectation for any function at all. And it's a beautiful theorem. And this is something that's really difficult to do it's not really difficult, but it's clumsy and not great for maximum likelihood type problems. But it's extremely elegant for Bayesian problems. If you think you can plug anything in here and you just take the mean of it, the empirical mean of it, across all of your samples, and that gives you this estimate of this expectation. So you can do things like compute the mean, you can compute the variance, and that's just the start, really. You can, if you're doing risk modeling, you can compute the probability that the risk is bigger than 1.5. The relative risk, say, is bigger than 1.5. And that's a really nice thing to do because it captures both the mean and the variance around that estimate of the risk. By including utility functions, as if your f in this theorem is some kind of utility function, You can do cost analyses, predicting losses and gains of things with uncertainty. So it's a really very powerful, this is probably the most powerful thing about Bayesian analysis. And with frequentist analysis, you have to go through a process of approximations, normal approximations, which essentially are only approximations, but you get the exact answer, unbiased answer, through the Bayesian method. And that's one of the really nice things about it. And I suppose this kind of brings me on to the next section of the talk, which is why be Bayesian at the end of the day. I mean, I don't want this to feel like it's a frequentist versus Bayesian thing, because I don't really like the verses. I don't really mean it's a competition. But why would you want to be Bayesian? And there are drawbacks, and I'll talk about those as well. So probably the first reason is that you might want to actually genuinely have some prior information that you need to combine with some data. And Bayesian methods are a principled way of doing that. Frequentists will agree with that. So I'll come back to that slightly later on, more formally. So Bayesian methods, if you start to kind of go into this area, you really find yourself thinking about the model all the time, and that kind of becomes the center of your thinking. And although, in a sense, the same is true of frequentist methods, I think you've got to have had a really good training in that, and not the kind of training that I received personally in my school and early university career in this area, which was just focused on normal distribution theory and statistical tests. You've really got to start thinking about the model. Bayesian methods force you to think about the model in kind of ways that you don't normally do as a frequentist. And because it gives you this flexibility to fit much more complicated models. So, yeah, and so it is easier if you've got a good algorithm to fit these more complicated models and hence, fit, more realistic data sets. You don't have to rely on asymptotic approximations like the mean plus or minus 1.96 times the standard error. I mean, there's only so many times you can see that before you get sick of it. For me, it was very early on. And that's perhaps why the Bayesian paradigm appealed to me so much, actually, because it was a move away from that and just a move towards delivering inferences in a different way. So the third point here, inferences are based on probabilities. We deliver a probability distribution. You can answer what's the probability that your parameter was bigger than a certain amount. And probabilities are quite easy to interpret. I mean, if you think about the dice example earlier on, everyone understands, almost everyone understands a probability. And everyone with some basic training is capable of understanding that. And so therefore it's a nice way of communicating the results of an analysis. So you can estimate any function of parameter, the expectation, that should say the expectation of any function of parameters directly. And that's I can't really explain just how powerful that is, but it's an extremely powerful part of this. Bayesian methods actually share a very similar asymptotic theory to frequentist methods, which means that as you collect more data, that there is convergence to the MLA, and it's kind of in that sense it's similar, and the reason for that is because the likelihood eventually dominates the prior. There are cases, again, more complicated cases where it's probably not worth going there. So as I mentioned, you can build model selection into the inferential framework, Bayesian model averaging, Bayesian model selection, model choices, again, are really elegantly solved in the Bayesian paradigm. And you could fit really complex models with one algorithm. I say straightforwardly, it's not straightforward. You're basically swapping one set of problems for a different set of problems with this. With maximum likelihood methods, it might be difficult to solve a complex problem because it's high dimensional. And optimization, so finding those best parameter combinations, is really hard. There's no solution to that problem. Now, when you accept the Bayesian framework, you still have to produce samples from the posterior, and that in itself is not necessarily an easy thing to do. Although these days there are really good algorithms for going out and Stan implements some of those algorithms. So why not to be Bayesian? Well, I mean, one argument against this is that the choice of prior is subjective, and it's definitely the case that different priors lead to different results. That's just analytical. Computational cost is typically higher. So and I'll talk about a little bit more about this in the next section as well. But the computational cost is a bit higher compared with frequentist methods. And there's some debate as to the meaning of the probabilities that come out through a Bayesian analysis. However, both sides would agree that if P of theta is your prior, then the posterior is how your beliefs should change if given the data. What they would debate is whether these are real probabilities. And there's some good reason for that. I think it's a beautiful area to engage with, but it does require some engagement with the literature. Okay, so when and how to be Bayesian. How much longer do I have left, Cameron?
If you can, maybe 10 more minutes, is that all right, Ben?
That's perfect. Yeah, that'd be brilliant. Okay, thank you. So when and how to be Bayesian. I mean, if unlike me, you find yourself being dogmatically Bayesian, fully believing in this paradigm and nothing else is correct, then that's fine. You don't need to worry about why you should be Bayesian. Just go and be Bayesian and enjoy that circle of like-minded devotees. However, if your viewpoint is a bit less extreme, and you sometimes want to, like myself, you sometimes want to do Bayes, you sometimes want to do frequentist, you might want to think about the following things. Well, can your model be fit quickly and simply using maximum likelihood? And can it be fit quickly and simply using Bayes? There might be a time limit to how long you've got to undertake your analysis. So you need to consider those things. I mean, the example of the linear regression above was easy. And I'm going to say these days, 5 years ago, 10 years ago, it wouldn't have been as easy. With WinBugs, tools like WinBugs, it's relatively easy to do this, but there's still a bit of playing around. The Stan code that I used to fit the linear model was really straightforward. It was just one line. Just like it was. Sorry.
WinBugs for me.
WinBugs, yes. Yeah.
It's still difficult for me, Ben.
Okay.
Not for me though.
Yeah. So WinBugs, does require some engagement. You have to write down the model. You have to write down the priors. I mean, I picked off Stan. I picked out the default priors. I just bunged it in, and that isn't really the way to conduct a Bayesian analysis. It should be done with a lot more care than that, really. You might want to consider what sorts of things that you need to report back on with your analysis. If you want to, be reporting using probabilities, then perhaps the Bayesian framework is more applicable. Do you love MCMC? Or I mean, perhaps you haven't tried it yet, but if you go and try it, you might think, yeah, this is great. This is the best thing since sliced bread, which is more or less what I thought when I first came across it. I thought this is great. Well, you need to tinker with your model. We need to change it in ways that are not implemented in maximum likelihood, are not available through standard R packages that fit these things through ML or something equivalent. Do you need to derive complex summaries from your model? So feeding in cost rules or cost functionals and things like that. But the bottom line is you don't need to be one thing or the other. You can mix these methods in a sense freely within reason. You can't just say, oh, I didn't like my prior. Let's just. You can't flip back between the two. You just use your head is kind of the way forward there. So, if you haven't, come across this area, or if you haven't ever fitted a Bayesian model before, it's probably worthwhile before doing it just having some, Googling some stuff. There's some great tutorials on YouTube. But at the beginning, I'd avoid articles with a negative bias. Those are fewer than there used to be, but there are still some. but later on, interact with those, and then you'll be able to critique them. But the main decisions you need to make are regarding the priors, and this is kind of where my how to be Bayesian thing is going to be focused. There are different choices here. So some people like what are called conjugate priors, and these are priors that have kind of useful theoretical. This is the main choice you need to make as a Bayesian. What is my prior? The conjugate priors have useful theoretical properties. What it says is that the prior and the posterior have the same algebraic form if you choose the likelihood in a certain way. But there are only certain functions which this works for, and it's advantageous because it means you can do things exactly, and you don't need to use MCMC. You can just write down what the posterior is. But in a sense, tying yourself to a prior like that that's there for theoretical convenience is not, for me, it's not desirable, though some people are very happy with that. It's great for things like Gibbs sampling if you want to run Gibbs sampling. So WinBugs is a Gibbs sampling program. Uninformative priors are the things that everyone wants. Everyone wants to use an uninformative prior. They don't place too much emphasis on any part of the parameter space. That's kind of desirable because, in a sense, that alleviates some of the frequentist concerns about Bayesian analysis, about placing prior probabilities on certain areas compared to others. But there's a trade-off here because sometimes you can't use uninformative priors, and you need a tight prior in order to get your sampling to work. Again, this is a bit beyond the scope of the talk, but in a sense, it makes you need to ask your question. You need to ask yourself the question: is my prior vaguely sensible? And you can do that by simulating data from your model. And simulate parameters, simulate data from the model given those parameters, and you can look at the resulting data that's produced, and you think, does that look anything like my data set that I'm trying to analyze? If the answer is no, then probably your prior is wildly wrong, and you might want to think about changing that, because it may well cause problems. It might not. It depends how much information there is in the data on the parameters that you're interested in. Subjective priors, I think for the dogmatic Bayesians, this is where they would sit. But in a sense, all priors are subjective, and it's kind of an active research area. It's a prior elicitation, going out, speaking to experts, gathering information, and then turning that information into a set of rigorously defined prior beliefs. It's kind of an active research area. But that does mean putting informative priors on things usually. My main advice for if you're interested in being Bayesian is to get interested in MCMC. It's a beautiful subject, rich and it's fascinating. But you can use lots of other methodologies integrated into nested Laplace approximations. There's an inler package in R to do those for certain classes of model. You can use variational Bayes. Again, just go and fit some different models using Bayesian methods and continually ask yourself, okay, what if I want to tweak my model to do this different thing? How would I do it? And in a sense, you should ask that question for any model or any analysis you do anyway, be it frequentist or Bayesian. So just to finish up, Bayesian analysis has been, widely accepted as a kind of a valid inferential method for many years now. It's a really fun area to get involved in because of the interesting things you can do with the posterior density. And I don't have time to cover some of those. I could show you some of the work that I've done, but I had to make a choice in what I would talk about and what I would not. And I thought it better to give an introductory thing rather than an inspirational thing. But I'm happy to do the inspirational thing as well if that's something that you'd be interested in. So getting either WinBugs or Stan running on your PC and just playing around trying to fit some models. The great thing about those is they implement the MCMC algorithms for you, and it means you don't have to mess around with that side of things, which is rather technical, and allows you to focus on the modeling, which is, for me, the main reason to be Bayesian. So I think that concludes it. Thank you very much for your time.
Thank you very much, Ben. I think that is a brilliant, exciting presentations about Bayes. I think you can spend 2 days to speak on Bayesian, but to cram everything in 40 minutes is a challenge. But I think you did well. You did well. I think you have you are very experienced Bayes user. So excellent presentation from you, Ben. I think now what I'm going to do is to open the questions to the floor, and so if there are questions, feel free to unmute yourself and ask questions to Ben.
Dear Dr. Ben, Dr. Taylor,
Hi.
my
Hi.
name is Irfan. I'm from Universiti Kebangsaan Malaysia, UKM. That's a very interesting and captivating talk for me, and it's give me like a refresher on Bayesian because I did some sort of Bayesian work during my PhDs.
Excellent.
So I've seen that you have been using lots of stand there. I mean, it's based on the Hamiltonian Monte Carlo. So what's your experience with that? Because I think the Hamiltonian Monte Carlo, I mean, it's a bit um, difficult to the to the layman in terms of using that, especially those who don't have much experience in using MCMC. That's my first question, and my
Yeah.
second questions. In terms of prior elicitations, I've read some books on this, based on the works by Professor O'Hagan from the Sheffield Group, Certain Judgments. The elicitations, these are 2018 books, I mean, written by my supervisors before, Dr. Malcolm Farrow from Newcastle. I mean, in terms of constructing the prior, what is the best way in terms of if you have like so many experts in the area, when you try to elicit from them, what is the best way to construct the prior distributions? Because if we just use the uninformative prior for that, uh, or the other priors like the Jeffrey's prior, I mean that will defeat the essence of the Bayesian paradigm itself. And another question is, for an intractable likelihood, do you think that other methods, for example, approximate Bayesian computation (ABC) will be an alternative for other method that you see that you explored in your slides? Thank you.
Yeah, no, nice set of questions. So clearly you have some experience here. So on the first of those questions surrounding Hamiltonian Monte Carlo, yeah, I think that for me has been probably the most huge advancement, in particular the Riemann manifold Hamiltonian's work of Girolami and Calderhead back in 2010 was the seminal paper for me in the last 10 years. But researchers have built on that, and the algorithm that's implemented in Stan is a kind of a modified Hamiltonian thing. But yeah, I mean, why is interacting with that any different to interacting with the Gibbs sampler? For me, they're similar kind of levels of complexity. You fit the model. You have to look at the trace plots. You perform. Again, this is kind of beyond the scope of the talk. But you look at your trace plots. You look for pathological behavior in the sampler, and if it's there, then you either need to rethink your priors or you need to run the sampler for longer. The advantage of things like Winbugs and RStan is that they do have off-the-shelf implementations of these methodologies, and that's really great. It's kind of enabling for people to go out and actually use those methods. My PhD was in kind of a mix between sequential Monte Carlo methodology and adaptive MCMC. These aren't trivial areas to work in at all, really, and there's lots of brilliant researchers around the world that have made lots of theoretical gains, and yet when you come to analyze a real data set, that's when you realize where the flaws are, where the difficulties arise. Yeah, but tools like Stan, tools like Winbugs, I think they're great to get into the area. And for everyone, there's kind of a ceiling of interest, and for some people that will be the ceiling. and for others it won't. Now, the second question, which was on prior elicitation, this is not one of my areas of expertise. I will confess that. So my work has mainly been in the design of MCMC samplers for spatiotemporal log Gaussian Cox processes. That's where I've worked in for the last 10 years or so. So just designing adaptive MCMC stuff, not going down the Hamiltonian route for reasons that are just uninteresting for this seminar. Yeah, I'm not an expert in prior elicitation, so I'm sorry about that. So I don't know what the best method for eliciting priors would be. What was the last question, Irfan?
It's about the likelihood. I mean, in terms of intractable likelihood.
Yes. So yeah, that's right. So yeah, indeed. Yeah, ABC is great. During my PhD, I was doing some work with Tony Pettit on that, and working with people like Chris Stravandi from QUT. We didn't get anything published, unfortunately, but yeah, I mean, when the likelihood's intractable, yeah, you can use other Bayesian type methods. ABC, approximate Bayesian computation. That's really interesting. I don't have a problem with that.
Thank you very much for your response. Oh, yes, I have one quick question, because you said about your sequential Monte Carlo, the SMCs. I always wonder whether the SMC, the sequential Monte Carlo, has any, analogously similar to the concept of Kalman filter for the state space model in forecasting. Is there any connection between SMC and then the Kalman filter itself? Yes.
There is, exactly. Okay, so again, this is beyond the scope of the presentation, but yes, for stochastic dynamic models, so for dynamic linear modeling or dynamic generalized linear models or anything that evolves over time, you can use sequential Monte Carlo to solve the filtering recursions. Okay, so the Kalman filter is a solution to the filtering recursions for linear Gaussian models, whereas sequential Monte Carlo can be used for more general state space models.
Thank you very much.
Right. Yeah. Yes, I hate to break this interesting discussion, so I'm a little bit lost somewhere, somehow. Thanks very much for those questions, Irfan. I want to give Ben maybe 1 minute rest before I come back to you. And I want to invite the president for the Malaysian Associations of Epidemiology to say something, if he's still there. Prof. Rahizat, you still there?
Oh, can you hear me?
Yes, we can hear you clearly, loudly.
Yeah. Okay, so thank you very much, Kamarul, for this organizing these interesting sessions, and yeah, my appreciations to Dr. Benjamin for your very interesting knowledge sharing sessions tonight, which of course is maybe some of us will crack our head to understand, but I think this is a very good sessions, and I would like to thank the Epid and Stats modeling team for USM for inviting us to be the co-organizers for this. Okay, just to introduce my associations, we are basically we are a new associations formed within this year of 2020, and we are focusing more on the training, basically lifelong training. So we are going to organize more and more of these kind of sessions. So maybe in the future we would invite again Dr. Benjamin for another sessions maybe. So well, it was a very interesting sessions. Then I think we can continue with the QA sessions, more interesting, I think, with more questions. So thank you very much, Kamarul and Dr. Benjamin here.
And thank you too.
Thank you very much, Associate Professor Dr. Rahizat. He's the president of Malaysian Associations of Epidemiology, and a newly minted association, fresh. Sorry, excuse me. And for your information, I think Ben has been in the academic for many years, and he's interested, I think, if given opportunity, to maybe look for potential collaboration with with some of us. But I think I leave that to some other time. And I've got the slides from Ben. Thank you, Ben, for your slides. I'm going to share with those who are interested to get the slides. You can email me. I put my email in the chat box there. And the presentation is also available on YouTube soon. I think it's I think it's 9 it's 10:09 now. So I think what my last word is to thanks again Ben for the brilliant talk and excellent presentation.
Yeah, before that, may I ask some question, Dr. Kumar?
Ask question. Okay, I have to give Arifin a question. He is maybe waiting for a long time. Okay, go on, Arifin.
Yeah. Hello, Dr. Ben. Thank you for your brilliant presentation. Yeah. I have just a very simple question, quite general ones. In your experience, how do you introduce Bayesian methods to those unfamiliar with I mean, there are many people not very familiar with the Bayesian method. Actually, quite an eye-opener to us, actually. And second question is that in your slide, you mentioned that using uninformative priors is quite desirable to alleviate the concern of those familiar with the frequentist methods. But if you use uninformative priors, I think it's no longer not that as Bayesian as it's supposed to be. So, what is your comment on that?
Yeah, that's a very interesting question.
That's all for me.
Yeah, thank you. Okay, so on the first one, okay. So learning materials, that's a very good question. I did have a think about this before the presentation. It's difficult for me to recommend anything because something that I like you might not like that. I mean, these days there are loads and loads of YouTube videos that kind of explain things at various different levels. I would strongly encourage you just to look around. I'm trying to think if there's a Bayesian book. I mean, the classic Bayesian text is a thing called Markov chain Monte Carlo in practice, but it's somewhat dated now. It was written in the 90s, and it's somewhat mathematical as well. And I suppose, in a sense, a lot of the really good texts are aimed at that kind of audience. But if you don't have that kind of background, I think it's probably it's worthwhile, Googling stuff and looking on YouTube for videos that are at a level that you're comfortable with, and you can always progress. I'm sorry not to recommend anything specific there. On the second point, that's a really interesting point, and I kind of, I can see exactly where you're coming from with that. I mean, the reason as a Bayesian you might want to use uninformative priors is because it kind of pushes back against that frequentist objection to the prior itself. But I, I appreciate that. That might seem counterintuitive. The thing is that you can then make use of the Bayesian machinery, so you can make use of this ability to estimate expectations through simple sums of draws from your MCMC algorithm. It's back to this theorem. This is the big thing that makes it really appealing. But yeah, I think there are a good number of Bayesians that may object to that and would think exactly along the lines that you alluded to, that one should use informative priors. And the truth is that when you fit complex models, you end up using them, because if you don't use them, your chain doesn't mix, and if your chain doesn't mix, you can't make inferences. I mean, my strategy when it comes to that is just to use priors that are as uninformative tolerate in a sense. But that's probably not it's not. There's no rigor behind academic rigor behind that. You're kind of lucky if the level of uninformativeness is sufficient to convince an audience that it is still uninformative. But you can always, as I said, you can always resort to this kind of idea of simulating. If you've got a complex model, simulating from the prior, simulating from the model, conditional on those values, and that gives you a sense. Even if it's in kind of a hand wavy way about how informative your priors are, or how sensible they are for the data. But yeah, you're right. Somebody that really believed in this philosophy would want to use informative priors, and they would go perhaps out to kind of seek expert opinion. My personal pushback on expert opinion, and that's why I did put inverted commas around the experts there, is because some of these models are really quite complex, and a lot of the experts are not modelers. And so how would you, if you're an expert working in a particular, I don't know, applied area that hadn't had any experience of modeling, how would you put a prior on some obtuse parameter that's hidden away in a model? How would you actually, to do that? I mean, again, it goes back to simulating data. So you can do this. You can present. Does this look? You can present to the expert. Does this look like the kind of data that you would expect? That's one way of doing it. But without that, I wouldn't expect an expert necessarily to be able to put a prior on something. It's a whole research area. This. Does that answer your question? I hope so.
Yeah, thank you. And it comes back to how you elicit the prior. Yeah, that's the main concern. Yeah, thank you. Yeah.
All right. Thanks. There's. I mean, there is always the debate between the Bayesian and the frequencies, right? But I mean, I think that's hopefully that will motivate us to go and read more about this, and we have to understand that Ben did not have much time to put everything in the slide. So, but I really appreciate what Dr. Benjamin Taylor has done. A very exciting presentation, interesting, and hopefully eye-opening for most of us. And we are very grateful for your time, Ben. For your time, really grateful. And hopefully, this. We can communicate more later. Hopefully, this will not be the end of this quote unquote relationship. And I think I would like to wish you all the best and have a nice day.
Thank you. I'm really honoured by your invitation to present, Cameron. It's lovely to see you again, and thank you. Yeah.
Thank you very much, and thanks everyone for coming. And we got at 1.62 participants attendees for this webinar. So I think it's everyone's. I think it's interesting. To see so many people coming to this meeting. So thanks again, everyone, and have a nice day, Ben. All the best. Bye bye.
Thank you very much. Okay. Bye bye.
Yeah. Thank you very much, Ben. Yeah.
No worries. Thank you.
Yeah, I appreciate your presentation.
Thank you.
Bye bye.